Hi, we're Laidback Engineering, and welcome to the Shit Show. Hi, I'm Cody.
I'm Solomon.
I'm Arnaldo.
I'm Rob, and we're all mechanical engineering students, and this project is called What a Drag. The goals of this project were to design a car model that minimizes the drag force, as well as being able to withstand a 1 kilogram load placed on top of the model. This car model had to meet the required design specifications. These include a 50-gram weight limit, a total length of 150 millimeters, wheel spacing of 32 millimeters, a wheel base of 90 millimeters, and meet the minimum cab dimensions of 50 by 33 by 30.
For our design, we initially thought about making our model's base plate out of plasma cut aluminum, which would be ideal for the 1 kilogram load, but it would have exceeded the 50-gram weight limit. We then thought about using closed cell purple foam, as it would be easy to shape. However, it would have been difficult to create a smooth surface finish. So, we opted for a 3D printed design made out of PLA plastic. This was the best of both worlds, as it was easy to design the model using Fusion 360 CAD software. This enabled us to meet the load requirement without exceeding the weight limit.
So for our design, as previously mentioned, we decided to go with 3D printed PLA plastic. All of our models were CADed in Fusion 360. This is the model of the first iteration, and this is the model itself. We tried to keep the wheels inside of the body to reduce drag, and we made simple little holes only supported by the wooden axles. Unfortunately, this model did not meet the length requirements as it was less than 15 centimeters. For our second iteration, we corrected the length and made it 15 centimeters in length. This extra length allowed us to better streamline the body. However, when printing this on a friend's printer, there was an error, and so it didn't come out right. Luckily, we could use my printer, but for it to fit, I had to angle the front a little bit. This is what it looks like. For this one, obviously the improvements, we streamlined the front, and I added recessed wheel supports to better constrain the axle. Unfortunately, due to the model's increased width, there was significant flexure on the top surface when a load was applied, so we were worried it wouldn't hold the required load. So it was back to the drawing board. By the third iteration, we were fishing for ideas, but luckily we were hooked on the concept of adding extra support material.
With our third iteration, we decided to trim the wheel well liner to reduce the weight. We added a T-beam under the model to reduce flexure. In addition, we added a 10 millimeter diameter circle on the top, which is recessed from the body, to indicate the load point. Improving upon our third iteration, we decided to add a base plate to the bottom of the model to prevent air from flowing through the hollow body.
Throughout this project, one of the things we learned was the difference between pressure drag and viscous drag. We reduced the component of pressure drag by streamlining the vehicle, even though it slightly increased the frontal area. This improved overall aerodynamics by reducing the drag coefficient.
What we learned in this project applies to the fields of automotive and aerospace design, where lowering the drag coefficient improves fuel economy. This also applies to structural design, where you want to avoid catastrophic failure. That was Project What a Drag.
And remember,
Teamwork makes the dream work.